Hey y'all, this is Minnie talking about Learning Objective 4 from Class 11. List the steps in excitation-contraction coupling in skeletal muscle and describe the roles of the sarcolemma, transverse tubules, sarcoplasmic reticulum, and the thin and thick filaments. Be certain to include the roles of modulatory proteins such as troponin and trypomyosin and of calcium ions. So, when we're talking about skeletal muscle, we're talking about muscles with central nervous system innervation. So all of this starts with a motor neuron in the peripheral nervous system, relaying its action potential to the respective muscle fibers that it innervates. Motor neurons link up with muscle tissue sarcolemma, which is just a fancy term for the connective tissue that wraps around muscle fibers, and is very good at conducting electricity, at points called the neuromuscular junctions, or also called the motor end plates. The end goal of an action potential is neurotransmitter release, and this holds true of the neuron's involvement in EC coupling. When the action potential hits an axon terminal, it causes the release of acetylcholine. I have the local current flows drawn out on the diagram with arrows so that we can kind of follow along where the charges are going and why that's important. The motor end plate is riddled with ligand-gated calcium ion channels that are responsive to acetylcholine. And when they are bound to this neurotransmitter, the channel opens up and causes an influx of calcium cations, which causes another local current flow into the sarcolemma. This local current flow is carried throughout the tissue by the transverse, or also called the T-tubules. These are just tunnels that help carry the electrochemical charges to the sarcoplasmic reticulum. The sarcoplasmic reticulum is basically a very large calcium storage unit for the muscles because we don't want the calcium cations readily free floating in the cytoplasm. For a couple of reasons. One, there would no longer be a gradient for calcium to diffuse with, and then second, we would be probably in constant muscle contraction and we would be in a lot of pain, and we don't want that. So we need to sequester all of these ions into the sarcoplasmic reticulum with the help of calcium ATPases, which I drew out for clarity and accuracy, kind of at the lower end of the SR. And once the current reaches the sarcoplasmic reticulum, it's actually the use of a DHP receptor that moves or wiggles a little bit in response to this influx of ions. And this movement triggers the SR to open up and spill out all of this calcium into the cytoplasm. Now, this is where the action actually happens, and we can start muscle contraction. So I drew out calcium flowing out of the SR with this gradient to reach the sarcomeres, which are made up of myosin, the thick filament with myosin heads that I also drew out as like little frills on the side, and then actin, the thin filament that looms right above it. Now, myosin usually cannot readily bind to actin and pull down the fiber to cause a contraction because the binding sites on actin are blocked by a modulatory protein called trypomyosin, which in itself is in turn regulated by another protein called troponin. The big role of calcium and the result of the SR spilling out calcium is that troponin is responsive to calcium cations, and when these two bind, it shifts troponin over, which also moves trypomyosin with it and causes the binding sites on actin to be exposed, so now there's the ability for myosin to bind. But I'll let Preston talk more about cross bridges and power strokes.
Learning Objective 5 from Class 11, Skeletal Muscle EC Coupling and Mechanics of Contraction. Diagram the chemical and mechanical steps in the cross-bridge cycle and explain how the cross-bridge cycle results in shortening of the muscle. In step 1 of the cycle, the myosin head hydrolyzes ATP and becomes energized and oriented. The process of hydrolysis converts ATP to ADP and phosphate. The energy from ATP hydrolysis will create an angle change of the myosin head to a 90-degree angle. Additionally, this process must have calcium bound to troponin to move tropomyosin out of the way so myosin can bind to actin. In step 2 of this cycle, the myosin head binds to actin, forming a cross bridge. Directly after the cross bridge is formed, the phosphate will be released. This will lead to step 3. In step 3 of this cycle, the myosin cross bridge pivots, pulling the thin filament past the thick filament toward the center of the sarcomere. This is known as the power stroke. This occurs when the myosin is releasing the energy it gained during hydrolysis, which causes an angle change from 90 degrees to 45 degrees. After the power stroke, ADP is released and ATP is attached to the myosin head. In step 4 of the cycle, as the myosin head binds ATP, the cross bridge detaches from actin. This will lead back to the hydrolysis of ATP and will restart the cycle.